This video is for my Algebra 1 class. It's over lesson 38, simplifying expressions using the GCF. So ladies and gentlemen, we've got a few vocab terms to get down here, and then we'll get into the actual math. So first of all, we need to know what a polynomial is. And a polynomial is an expression consisting of variables and or constants that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents. So ladies and gentlemen, that's kind of a mouthful. Let's break that down. What does that actually mean? What is this definition trying to get at? And so essentially what the important part here is, if I go to my dry erase board, is I can have things like x plus 3, that's a polynomial. I could have just x by itself, that's a polynomial. You could have 2x squared plus 3x minus 5, that's a polynomial. One thing that you can't have, however, is you cannot have x in the denominator. That's not allowed. Now, if I had x in the numerator, that's no problem, because as we've talked about in previous lessons, we can reimagine this as 1/5 times x. And so you'll notice that the definition specifically leaves out division as a possible operation. This doesn't mean that if you have a fraction, it can't be a polynomial. It just means that a little bit of conversion would be needed. We need to convert this into a multiplication problem for it to be a proper polynomial. So the trouble with being in the denominator, though, is that you can't really just slide a 5 off and have 1 over x. It doesn't work the same, having 1 over x as a coefficient. So instead, what we could do here is we could look at this as 5 divided by x. Now you're not allowed to have division, so we have to change this to times the reciprocal. Now we're not allowed to have 1 over x because that would be division still. So I could make this into x to the negative o. But wait, if you look at our definition says non-negative integer exponents. So no matter how I try to get out of this, I've either got division or negative exponent. So really, the big takeaway here from this definition is no variables in a denominator. A monomial then is a polynomial just with one term then. So nothing being added or subtracted, it's just a single polynomial. You can have multiplication, that's fine. You can have exponents, that's fine. But no division. Division's not allowed. Or excuse me, no addition or subtraction for monomial. So today we're going to be taking a look at the GCF of monomials, so the greatest common factor of monomials. And this is the largest monomial that divides into each number with no remainder. And we're going to use a couple different techniques for how to find the GCF of two monomials. So here I have two monomials, 120 x squared y cubed z and 96 x to the fourth y z squared. So one way to find the GCF is to prime factorize both of these terms. So if I take my 120 x squared y cubed z, since we don't know what x is, what y is, what z is, we treat variables as if they're primes. So the only thing really that I need to break apart here is the 120. So if I break apart the 120, I might do this using a factor tree. 120, that'd be real nice for a factor tree. So 12 times 10. I know 12 then is 3 times 4. 3 is prime, so that's all done. 4 is 2 times 2. 10 is 2 times 5. And so if I put this all together, the prime factorization of 120x squared y cubed z would be, I got 3 2's, so 2 to the third power, times, I got a single 3, times, I got a single 5, and then x squared y cubed z. because we treat each of those variables as if they are their own primes. So for 96, x to the fourth y z squared, we could likewise use a factor tree to break that 96 apart, or we could use division by primes. And I'm only going to divide the 96, so that's why I'm stopping my little upside down division box right there. So looking at 96, 3 goes into both 9 and 6, so that's kind of nice. Goes in 32 times. That's nice and even, so maybe we do a 2 there. So I get a 16, do 2 again, I get an 8, 2 again, I get a 4, 2 again, I get a 2. We got all primes now. So put this together. I have 2 to the 5th power, 5 2's there, times 3. And remember, we do put our primes in order. So numbers before variables, though. So to find the GCF, what I'm going to do is I'm going to take each prime term, each prime factor, each prime factor, and I'm going to choose the lowest exponent, because the lowest exponent is what they have in common. So if you consider the 2's, for example, we have 2 to the 3rd power and 2 to the 5th power. The lower is the 3. These both have 3 2's in them. Now this one has a couple extra 2's, but they both have at least 3 2's. That's what we're going with, the least. We want to know what do they have in common. So they have 3 2's in common. So move over to 3's. Well, they both have just a single 3. And then over to the 5's. Well, this has a 5, but this doesn't have any. So they don't have 5's in common. Leave that out. Next up to the x's. So x squared and x to the 4th. I'm going to choose the lower of the two exponents. They both have at least an x squared. A y cubed and a y. They both have a y in common. This has 2 extra y's, though. And then finally the z's. They have just a single z in common. This one has an extra z, though, making it z squared. Now, put those numbers back together. So 2 to the 3rd power is 8 times 3 is 24. X squared y z. By the way, using this method, we can also easily find the LCM, and even though that's not this lesson, what we would do instead of choosing the smallest exponent, we would actually choose the largest exponent. If you choose the largest exponent, you actually get the LCM. And I know that seems kind of counterintuitive. Here we're looking for the greater, but then we choose the lesser of the exponents. It seems a little backwards, but if you think about it, when you're doing factors, factors are always going to be smaller than the number themselves. And so that's why we've got to choose the smaller of the two numbers. Whereas multiples are often bigger than the number itself. So it either is the number, because it's the first multiple, or it's bigger. So for the LCM, we go for the bigger exponent. So that's one method right there, using the prime factorization to help us find the GCF. Another method that we can use here, and I'm going to reuse the GCF of 120 x squared y cubed z and 96 x to the 4th y z squared. So another method that we can use here, and then there are tons of methods out there, but I'm just going to teach you two, is going to look a lot like division by primes. It's going to be an upside down division, but we don't specifically have to use primes here. So this other method, I'm going to take my two monomials, and I'm going to write them with just a little bit of space between them. And then I'm going to do an upside down division box. And I'm looking for something that will divide into both of these numbers here. So something that will go into both of these numbers. So, maybe we start with our variables. Maybe I start with x's. So I see that there's an x in both of these. Specifically, I think I can pull out an x squared out of both of those. So if I pull an x squared out of this, then that's all my x's gone. So it'll just be 120y cubed z. Over here I'll have a 96, and now if 2 are pulled out, I'll have 2 left over. And then just like division by primes, I'm going to keep going now. So let's do our y's. I just have a single y there, so I can just pull a single y out. So 120, pull a single y out, y squared, z. Over here, pull a single y out, that's all of them. So just z squared. Finally, if I do my z's, I just have a single z that I can pull out. And so I'll have 120 y squared, and over here 96 x squared z. Now if you look at your variables when we're all done here, these shouldn't have any variables in common. We've pulled out all of the common variables. So now let's start looking at the numbers. And so I might look at 120, I might look at 96, and maybe I know that 12 goes into both of those numbers. So let's just go with 12 for now. If I pull a 12 out of this, 12 goes into 120 10 times, so 10y squared is what's left over. 12 goes into 96 8 times. All right, now I see that there's still more that I can pull out of both of these. With a 10 and an 8, I can still pull out a 2. And so I'm going to get 5y squared, and I'm going to get a 4x squared z. All right. Anything else I can still pull out of there? Well, no. So if there's nothing else I can pull out of there, then all the stuff on the outside is my GCF. So put that together then. 12 and 2 makes 24. And then I have an x squared, a y, and a z. And if you compare our two answers, we got exactly the same thing. So 2 different methods. I don't really care which one you use as long as you follow the directions in the book. So if the book tells you specifically to use prime factorization, you do need to practice using that. If not, this can be a nice little trick. For that matter, I wouldn't mind if you were to kind of do all your variables at once. So I'll do that on my dry erase board here. I won't make you copy it down again. So if I took my 120 x squared y cubed z and my 96 x to the 4th y z squared, I might look at this and say, okay, I got an x squared I can pull out, I got a y that I can pull out, I got just a single z I can pull out. And so if we do that then, okay, I'm still going to have my 120, but now my x squareds are gone. I'm going to miss a single y now, so that'll be a y squared. And then my z will be taken out. That's gone. Okay, so come over here, pull out an x squared. That'll leave an x squared. Pull out the y, he's gone. Pull out the z, and we'll have just a single z left over. So you could pull all your variables out at once. And then from here, let's say you're familiar with the fact that 24 hours is 1 day, 48 hours is 2 days, 72 hours is 3 days, 96 hours is 4 days, and 120 hours is 5 days. Well, then you'd recognize that 24 goes into both of these, goes in there 5 times, goes in there 4 times, and there's nothing else I can do there. And I get my answer a bit faster. By the way, while we're looking at this here, we talked about the fact that the outside stuff gives you the GCF. Well, one thing that's nice about this technique right here is if I combine the outside stuff with the bottom row, it gives you the LCM. So that's a nice little trick there. You get to the LCM and the GCF quickly. So again, ladies and gentlemen, I don't really care which of these 2 methods you use generally, whichever you find easier. So let's go ahead and flip the page over here. And we're going to talk now about the not GFC, GCF of a polynomial. And so since we're not saying of a monomial, it can be assumed that we are allowed now to add and subtract terms together. So this equals the GCF of its monomial parts. So in other words, if you were to break it apart into monomials, then the GCF of those monomials would be the GCF of the original polynomial. So therefore, if I asked you to find me the GCF of 120x squared y cubed z plus 96x to the fourth power y z squared, well, on the front we just found the GCF of these two monomials a couple times. So we already have done the work to know that the GCF of this polynomial must be 24x squared y z. Now, ladies and gentlemen, it is not always required that you use the prime factorization or you use that upside down division box. Sometimes it's going to be much easier than that. For example, we're going to find the GCF of 6x cubed minus 15x squared plus 30x. So if we consider what we did here, this is actually a lot like reducing a fraction. You're looking at what can both of these be divided by, what can both of these be divided by, what can both of these be divided by. So a lot like reducing a fraction. So if we think about it that way, what can I reduce each one of these by? So let's just start with the numbers. So I got a 6, I got a 15, I got a 30. What's the biggest number that goes into each of these? Well, obviously with a 6 and a 15, 3 goes into that. Well, 3 also goes into 30. Okay, can you get anything bigger though? Well, think it through. Not really. So the only thing bigger than 3 that goes into 6 would be 6, which is fine with the 30, but doesn't work with the 15. So 3 it is. 3 is the biggest number I can get into each of those. Now look at the variables. I got an x cubed, an x squared, and an x. What's the biggest variable then that I can pull out of each of these? Well, I can pull a single x out of each of these. So the GCF of this is just 3x. So let's say I asked you to find the GCF of 16 a to the 5th power b squared c to the 4th power plus 48 a cubed b to the 6th c to the 4th. So go ahead and pause the video and see if you can figure this one out for yourself. All right, let's see how you did. So with a 16 and a 48, you might be tempted to say, well, 8 goes into both of those. 8 goes into this 2 times, 8 goes into that 6 times. Well, if you think about it that way, could you reduce, if this is a fraction, could you reduce it more? Well, yeah, you could. You could still pull a 2 out of them. So that means 8 is not the biggest thing that we can pull out. So it turns out the biggest thing we can pull out of both of these is 16 itself. 16 goes into 16 once, 16 goes into 48 3 times. Now look at your a's. The most you can pull out of both of these is an a cubed. I will take all of these, but there'll be 2 left over there. The most you can pull out as far as the b's goes is a b squared, and we can pull a c to the 4th power out of both of those. Let's try GCF of 49r minus 63t plus 91u. So go ahead and see if you can do this one. Pause the video. All right, let's see how you did. So 49, 63, 91. Just take the numbers first. And sometimes when there's three terms, it's good to just start with two of them. So like 49 and 63. So 49 and 63, what can I pull out of both of these? Well, I could pull a 7 out. So let's consider, can I pull a 7 out of 91 as well? And yes, we can. It goes in 13 times. So it would go in here 7 times, it would go in here 9 times, and then 13. So with a 7, a 9, and a 13 left over, is there something that we can pull out of them still? Well, no. So 7 is my number. Look at the variables now. Can I pull, how many r's can I pull out of each of these? Well, none. These two don't have any r's. Same thing with the t's. These two don't have t's. Same thing with u's. These two don't have u's. So there's actually no variables that we can pull out of this, because each term would have to have that variable. So therefore, the GCF of this is just 7. Let's try the GCF of 32, g to the 7th, h to the 3rd, minus 75, g to the 5th, h to the 5th. Go ahead and pause and give it a shot. All right, let's see how you did. This is one where prime factorization might be helpful. You might have it memorized that 32 is 2 to the 5th power. We know that 75 is basically like 3/4. Well, 3 times 25, or 3 times 5 squared, would be its prime factorization. So if we look here at our numbers, there aren't any prime factors in common, which means that the greatest common factor between 32 and 75 is 1. Now, of course, if we have 1 in front of a variable, that 1 will disappear. So can we get any variables? Yes, we can. So we got a g to the 7th power and a g to the 5th power. That means you can pull a g to the 5th power out of each of these. Look at your h's now. I got an h to the 3rd power, h to the 5th power. So I can pull an h cubed out of each of those. So my GCF is just g to the 5th power, h to the 3rd power. So ladies and gentlemen, we're now going to use this to help us factor. So let's go back to our 6x cubed minus 15x squared plus 30x. So one of the things that the GCF allows us to do is to completely factor this statement. So the GCF from up here, I'm just going to grab a color. I happen to grab purple. The GCF was 3x. So that means I can pull a 3x out of here. And it will go into each of those without a remainder. So 6 divided by 3 gives me a 2. X cubed divided by x gives me an x squared. Minus 15 divided by 3 gives me a 5. X squared divided by x gives me just a single x now. And then 30 divided by 3 would be 10. And then x divided by x cancels, it's gone. And so we get 3x times the quantity, 2x squared minus 5x plus 10. So let's try factoring our second statement up there, 16 a to the 5th power b squared c to the 4th power plus 48 a cubed b to the 6th power c to the 4th power. So I'm going to grab a different color this time. I happen to pick up my green. So we've already discovered that the GCF of this is 16a cubed b squared c to the fourth power. So that's what can be pulled out of each of these terms. So what's left behind? Well, 16 divided by 16 would be 1. So if there's any variables, that 1 will disappear. A to the fifth power divided by a cubed would leave behind an a squared. B squared divided by b squared is going to cancel, become a 1. And c to the fourth divided by c to the fourth will also cancel. So we're left with just a squared. So plus 48 divided by 16 would give me a 3. A cubed divided by a cubed cancels, that's gone. B to the sixth power divided by b squared gives me a b to the fourth power. And finally, c to the fourth power divided by c to the fourth power will cancel, that's gone. So factored, this is the GCF 16 a cubed b squared c times the quantity a squared plus b 3b to the fourth power. All right, next up, 49r minus 63t plus 91u. And we already know that the GCF here is 7. I happen to grab my pink highlighter this time. And so if I pull a 7 out of this, 7 out of 49 is 7, still has the r. 63 divided by 7 is 9, still has the t. And then 91 divided by 7 is 13, still has the u. All right, last one from above, 32 g to the 7th h cubed minus 75 g to the 5th h to the 5th. So this time, let's see, I guess I'll grab my blue. We know that the GCF is g to the 5th power h to the 3rd power. Times the quantity. Well, no numbers are being pulled out, so that was a 32, it's still a 32. However, I'm pulling out 5 g's, so only a g squared will be left. And then h cubed, well, the h cubed is going to be gone. Minus 75, and then if I pull 5 g's out, the 5 g's are gone. Pull out 3 h's, 2 h's are left. So g to the 5th power h cubed times the quantity 32g squared minus 75h squared. So ladies and gentlemen, we're building this all up to a skill that we're going to be using throughout our math careers moving forward. So let's just go to a new sheet of paper here. We're going to go to a new concept. Let's go new sheet of paper. And I've got my new sheet of paper all set here. If you need to pause to catch up to me, go ahead and do that. So our next term that we need to be aware of is what's called a numeric fraction. We're going to make it plural for the sake of the sentence. Numeric fractions are fractions, but we're not going to leave it at just that. Numeric fractions are fractions, and as the name suggests, numeric, with only numbers. So for example, numeric fractions, 6/15, 9/18, 28/7. Those are all numeric fractions. And I specifically chose these because they're all reducible. And when we reduce, we typically look for the largest factor of each of these, or in other words, the GCF. So what's the greatest common factor between a 6 and a 15? Well, obviously that's 3. So imagine dividing this by 3 over 3, and we know, of course, that this reduces to 2/5. Or if you consider between 9 and 18, the GCF would be 9 itself, because 9 is a factor of itself. This will reduce completely to 1/2. And then 28 and 7 share 7 as a factor, which of course 28 divided by 7 then would be 4. 7 divided by 7 would be 1. And so of course, I mean, this is really 28 divided by 7. It's 4. Grab your yellow highlighter. Numeric fractions, that's a vocab term. So now we're going to take a look at algebraic fractions. And algebraic fractions contain variables. And this is a vocab term, so we're going to highlight that in yellow. Algebraic fractions. So an example of an algebraic fraction, if we borrow from the work that we've already done, 120x squared y cubed z over 96x to the 4th y z squared. So ladies and gentlemen, if we imagine dividing this by its GCF, which we figured out was 24x squared yz over 24x squared yz, we should be able to reduce this algebraic fraction completely. So 120 divided by 24 is 5. X squared divided by x squared cancels. Y cubed divided by y gives me y squared. And z divided by z cancels. So on the bottom, 120 over 96. We know that 120 will reduce down to 5 when we divide it by 24. 96 divided by 24 reduces down to a 4. X to the 4th divided by x squared gives me an x squared. Y and y just cancel each other out. And then z squared divided by z is z. If we can consider 6x over 15, slightly easier. The GCF here is 3. So if we reduce this, 6x divided by 3 gives me 2x, and 15 divided by 3 gives me 5, which of course then would be the same as 2/5 x. So let's take a look at some, oh, just kidding, not yet. Sorry guys. We'll do a couple more examples here. Let's say we had 9 over 18x. I mean, it's obvious that I can't pull an x out of both the numerator and the denominator. However, we could divide this by 9 over 9. And so 9 divided by 9 would be 1. 18 divided by 9 would be 2. And the x is just trapped there in the denominator. This would not be a polynomial. However, it would be reduced. If I had 4x over 4, well, same idea. I know that 4 goes into 24 6 times, and 4 goes into itself 4 once. So I could divide this by 6 over 6, and then, well, there's just a single x in the top. And so this would be 4x. There's going to be 6. Oh, goodness. What was I doing here? Getting ahead of myself. That's what I was doing. Sorry. Divide this by 4 over 4. There we go. I knew something didn't seem right. So 24x divided by 4 would be 6x. 4 divided by 4 would be 1, which really then is 6x. So if the variable's in the denominator, it's going to be stuck. If it's up top, it can either slide off the side like this 2x over 5, or the whole thing will just come down because it's over 1. All right, dashed line now. So ladies and gentlemen, one of the places that we use this in particular is reducing fractions such as this. So we want to factor both of these as much as we can. Well, the denominator is just a single number, so there's really no factoring there. But up top, we can, well, with this 10 and a 6, I can pull a 2 out of both of those. Leaving behind a 5x minus 3. And then this is still over 8. Well, now we have some multiplication here. We have 2 times the quantity. So since it's multiplication, I can reduce the 2 with the 8. So this will become a 1, that will become a 4. And now 1 times the quantity, it's really just the quantity. And then on bottom, we have a 4. And so that would be completely reduced. Let's take a look now at 6x squared over 15x. I'm going to pause right there before I even try to simplify this further. We know that denominators of fractions cannot be 0. That means that 15x cannot equal 0. Well, you can solve inequalities like this just like you solve equations. So if we divide both sides by 15, what we really discovered is that x cannot be 0. So as I consider what goes into both of these, well, with a 6 and a 15, 3 goes into both of those. With an x squared and an x, I can pull out an x from both of those. And so my answer then is, well, 6 divided by 3 is 2. X squared divided by x is just x. But then over here, 15 divided by 3 would be 5. And then x divided by x would cancel. And so that is as reduced as it can get. Now, if you take a look here, we know that in the original problem that x could not be 0. So what we need to consider is, in this simplified version, is x able to be 0? Because if it is, that doesn't match the original, and so we couldn't use that. Well, it turns out if you plug in 0, you get 2 times 0, which is 0, and 0 over 5 is just 5, or excuse me, is just fine. That's 0. So yes, this 0 could be used here, but we're not allowed to use 0. So what we've got to do is we have to add on here a semicolon, and we're going to mention the excluded value. So we are excluding 0 as a possibility here for x. So if your final answer doesn't show this kind of a restriction, we have to mention it. So let's try 12a squared b plus 12a b cubed. Oop, my fraction bar went a little crazy there. All right. Oh, sorry. make that first 12 a 24. And we're going to divide this polynomial by 3ab. So pause real quick here. We know that the denominator, 3ab, cannot be 0. Now here's the thing. Since this is multiplication, the only way it would be 0 is if either 3 was 0, or a was 0, or b was 0. That's the only way that this could equal 0. So as long as none of these three things are true, then we're all set. Well, 3 is never equal to 0, so there's no problem there. A not being equal to 0 is something we're going to have to watch out for. B not equal to 0 is also something we're going to have to watch out for. So if we simplify, first I'm going to factor. So with a 12 and a 24, I can pull a 12 out of both of those. I can pull a single a out of both, and I can pull a b out of both. So pull a 12 out of 24, I get a 2. Pull an a out of a squared, I get an a. Pull a b out of b, the b's are gone there. So plus, pull your 12 out, pull your a out, pull your b out, well, there's going to be a b squared left over. And that will be over 3ab. Well, 12 and 3 can now reduce because this is now multiplication outside the parentheses. So it's multiplication times parentheses. So 3 goes into 12 4 times. 3 goes into itself once. Now the AB, the A on top will cancel the A on bottom. The B on top will cancel the B on bottom. So with all ones on bottom, this is basically going to be like a whole number. So I'm going to have 4, and let's go ahead and distribute this 4 back in. So 4 times 2 will give me 8a plus 4b squared. So consider here, is there anything that would cause a to not equal 0? So if you plug in 0 for a, does that cause a problem? No. So we do have to mention that a cannot be 0. So likewise with b, if we plug in 0 for b, does that cause us some trouble somewhere? Well, no. So we do need to mention b as well, cannot be 0. All right. One more example. This one's a little bit more involved. So let's flip to the back. And for our last example, we have 5p cubed, q cubed, r cubed, minus 20p to the 5th, q squared, r. Ten p squared, q r squared, plus 20 p squared, q squared, r squared. So first things first, let's actually factor this time. So up top with a 5 and a 20, obviously I can pull a 5 out. I can pull a p cubed, a q squared, and an r. And so when I pull a 5, a p cubed, a q squared, and an r out, I have a q r squared left over up top. Next, pull a 5 out, I get a 4. There'll be a p squared left over. q cubed, oh sorry, not q cubed, 20 divided by 5 will give me a 4. P cubed out of a p to the 5th power gives me p squared. Q squared, cancel. R and R cancel. And that will be over. With a 20 and a 10, I can pull a 10 out of both of those. And then a p squared out of both of them. Q and an R squared. All right, and what's left behind? Well, that's all of this first term. So if we divide something by itself, we get 1 plus 20 divided by 10 is 2. P squared divided by p squared cancels. Q squared divided by q gives me a q. And R squared cancel. So let's see what we can reduce now. With a 5 and a 10, I can reduce those down to 1 and 2. With a p cubed and a p squared, I can reduce those down to p. With a q squared and a q, I can reduce that down to a q up top. And finally, r with an r squared, I can reduce that down to an r on bottom. I'll line up a new equal sign with an old one and keep moving from there. So 1 times pq really is just pq times qr squared minus 4p squared. Next up, we have a 2r times 1 plus 2q. No more reducing before multiplying. Now we did this one a little out of order. This time, what I'm going to do though to find my excluded values is instead of taking this, it can often be easier to pull our factored version. So the denominator, 10, p squared, q, r squared, times the quantity 1 plus 2q, well then we can start splitting this up, because in order for this to equal 0, in order for that denominator to be 0, something that we're multiplying has to be 0. So we got to make it not equal to 0. So obviously 10 is not equal to 0. That's not even really worth mentioning. So, I'm sorry, not p squared. So I just want to know p cannot equal 0, because if p is 0, the whole thing's 0. Same thing with q then. Same thing with r. Sorry guys, having some trouble writing today. So now there's a fourth option here. So the fourth option is the quantity. So if that equaled 0, then my denominator would be 0. So we want to find out where is this not true. So I could subtract 1 on both sides, leaving me with 2q is not equal to a negative 1. Divide both sides by 2. And Q then is equal to a negative 1/2. So looking back up here, I want to know, are these values still restricted in the reduced form? So is there any problem with P being equal to 0? Well, not as far as that denominator goes. So therefore, we do have to mention that P cannot be equal to 0. So could Q be 0 here? Well, here Q is 0. 2 times 0 would be 0, plus 1 would be 1. So it doesn't look like that's really going to cause a problem in the reduced fraction. So we do need to mention it here. And then, will R cause a problem? Well, yeah, it will. If R is 0, 2 times 0 is 0, and then times the quantity would be 0, and we'd again have an undefined problem. So we actually don't have to mention that. You can if you just want to be safe, but you don't have to mention that because, well, sorry, add a couple more lines in there. You don't have to mention it because this reduced form still has R in the denominator being multiplied. And then finally, if Q is negative 1/2, I would plug Q in here and see how it goes. So 2 times a negative 1/2 would be 1. A negative 1, excuse me, a 1 plus a negative 1 would be 0. And then 0 times anything is 0. That causes a problem. Well, we already knew that. So since it's still saying that Q being negative 1/2 is a problem, we don't have to mention Q. And that, ladies and gentlemen, is the end of this lesson.